Hi, everybody. Welcome to SharkFest 2020 virtual. This is all new for me, actually. I prefer to be in person talking to you all face to face. But this is the next best thing we've got. So I'm super excited about this. I sat in Sake's presentation yesterday, his 8-hour class yesterday about TLS. It was fantastic. My intention here with this class is to give you a down and dirty, simple approach to understanding what's happening with TLS encryption and decryption, effectively what every engineer should know about TLS. Now, the way I'm going to run this session is if you have questions, use the Q&A. Natalia will help me figure out which ones which questions need attention. I may have some questions for you where I ask you to raise your hand throughout the presentation. Otherwise, please feel free to ask questions. I really want you to walk away with this with an understanding of what's happening with TLS, especially if I can give you some visuals to help you get that understanding. So let's get started. So my name is Ross Bagurdes. My primary work is creating training videos for Pluralsight, as well as doing other types of training and other types of engineering consulting. You can find my work at pluralsight.com. Our goals for this session. First, I want to talk about the difference between SSL and TLS. All right, I want to explain what's one versus the other here. I want to then talk about encrypting data and the basics of encrypting data. I want to talk about the Diffie-Hellman key exchange, and I want to talk about it in a way of actually looking at the mathematics of how that works. We're going to look at the data encryption protocols we use to actually encrypt our data using HTTPS or using TLS in general. We're going to look at the TLS 1.2 and 1.3 handshakes. We're going to find out what TLS 1.3 brings to the table for us. And then last, we're actually going to do some work in Wireshark itself. We're going to take a look at some of those handshake messages, as well as learn how to capture the session key so we can decrypt our traffic in Wireshark. So let's get started. So first things first, I have a OneNote where you can, if you write this down and link to it, you can see my OneNote notes. And I'll bring that back up in just a sec. It's right here in my OneNote itself. I have a list of where you can find me on Twitter, my email address, my courses at Pluralsight. I have links for TLS Illustrated 1.2 and 1.3. These are really fantastic. That goes through and it annotates every component of every field of the TLS handshake. It's really impressive. It just takes a lot of time to go through these. And then I also have some captures that I'm going to use in my presentation here that you can link to as well. So I'll leave that up for a second. Actually, let's just copy that right into the chat window. Copy. And let's put it over here. All right. So web browser encryption. When we're talking about web browser encryption, of course, we're talking about using HTTPS. And there are really two major components happening there. The first one that we are going to talk about is negotiating the encryption session. The other one is encryption protocols used actually to encrypt our data between our client and our server and back again. So to negotiate that encrypted session, we're either going to use SSL or TLS. And I'm going to talk about the differences between those in just a second. Then we're also going to use encryption protocols. And these are the big ones that we're going to use here. There's actually a few more that are supporting cast members for these encryption protocols. But we're going to use one of these encryption protocols. The three on the left, RSA, Diffie-Hellman, and elliptical curve Diffie-Hellman ephemeral, ECDHE. Those are asymmetric encryption. The ones on the right, triple DES, AES, and SHA-20, those are symmetric encryption protocols, which are actually going to do the bulk encryption of our data. So where did this all come from? And why SSL versus TLS? Well, back in '94, we have Netscape Navigator coming out. Now, Netscape Navigator was pretty revolutionary. I was in college when this came out, and it was pretty fantastic to have this real simple interface to navigate the World Wide Web at the time. It was brand new. It was mostly text-based, but it was still cool to have this. Businesses quickly caught on to the value of this web browser and HTML, transferring HTML documents using HTTP. So Netscape Navigator developed SSL. And SSL version 1 was never released. SSL version 2 was the first one. Very quickly, they discovered that there was a problem with SSL v2 and fixed the problem in 1995 to SSL v3. Now, something else happened in 1995. I'm sure if you were around then, you may have remembered getting the stack of floppy disks, of like 30 floppy disks to install it on your computer. And that is Windows 95 came out with the famous Internet Explorer, right? And what happened after that, right? What happened right after this began is Microsoft started to really push that Internet Explorer was a function of the operating system, and the browser wars began, right? So here, shall we play a game? And Microsoft said, yes, we should. Well, what does it have to do with SSL and TLS? Well, by 1999, we needed an update to SSL, and Microsoft wanted nothing to do with the name SSL because Netscape gave SSL that name. So in order to accommodate Microsoft's desires, the name was changed. Now, SSL and TLS, these are all RFCs managed by the IETF. So this is all public information. So Microsoft played its hand. They were able to get the name changed to TLS. So instead of secure session or secure socket layer, now we have transport layer security. And even until recently, Wireshark, you had to type in SSL to do all of your querying, even though SSL was pretty much outdated back in the late 90s or the early 2000s. So TLS is the primary name now that we're using. We have TLS version 1.2 and TLS version 1.3. Now, does that mean that SSL is gone? No. The names are really interchangeable, SSL and TLS. It's the same thing. I've read some things online where it said SSL is only used for this one thing and TLS is only used for this other thing. That's generally false. They're the same protocol, just different versions of it. And if we're using anything less than TLS 1.2 at this point in time, we should really be upgrading to that. If you have a security audit done on your systems and they see anything less than 1.2 being used, they are definitely going to recommend that you change that protocol. So, data encryption basics here. We talk about data encryption. Typically, there's lots of ways to encrypt communication, but when we're talking about using TLS to encrypt the actual data, to encrypt the website information, to encrypt our credit card numbers, our usernames, passwords, things like that, what we're using here is a symmetric encryption protocol, right? So we're going to take our message and we're going to run it through an algorithm like AES or SHA-20 along with a unique session key, all right? And that key plus the algorithm is going to allow us to encrypt our message. Once the message is encrypted, now we can send it across a public channel where no one's going to be able to decrypt it, theoretically. Once it arrives on the server, we can then take the same algorithm that we use to encrypt it along with the same key and decrypt our message. Once our message is decrypted, now the server can respond to it if it's a GET request or whatever we're doing here. The challenge, though, is that we can't send our session key over the public internet, because that would mean anybody on the public internet could get access to the session key, which means that they could decrypt our data. So how do we resolve that? Well, this is where key exchange protocols come into play. So the key exchange protocols that we're going to use here, these are going to be used to actually generate a key that we can use for AES or Cha-Cha-20. Now, this part of the process is one of the more complicated parts. And it's often, when you look up information about how TLS works, it often focuses on this key exchange process instead of focusing on the big picture of what's happening with TLS. So you might hear somebody say something like, oh, I know how TLS works. The public key in the certificate encrypts the data, and then the server's private key decrypts the data. Well, one, we're not going to use RSA anymore, and because it has some issues with its implementation. And two, that's only part of the process. So what do we want to do here? I want to show you how the key exchange process works. Now I'm going to show you how Diffie-Hellman key exchange works. We're also going to look at the elliptical curve process as well. But I think the Diffie-Hellman process is pretty cool because the math isn't very complex. It's pretty simple math. So let's go through how this works. So in order to get the same key on both the client and the server, we're going to do some trickery with prime numbers. Now, included in the certificate that we're going to use through our TLS process, there are two numbers in there, a P value and a G value. These are prime numbers. These are going to be really big prime numbers. I've chosen two small prime numbers to make this easier. So we're going to send that certificate from the server to the client at some point during the TLS handshake. If we're using Diffie-Hellman for the key exchange, the client then is going to take the P and the G value and realize that that is the public key information. The client is going to have a private key selected that's going to sit in memory. And that private key then we're going to take and run it through a formula. And the formula is this. We're going to take the G value from our public key. We're going to raise it to the power of our private key. And then we're going to do this mod operation on it. And a mod is a modulus of P. Well, what is this modulus? Some of you, if you've studied mathematics, you'll likely very clearly know what this is. The rest of us may have to go back to third grade math to understand it. So let's do our third grade math lesson here. Whoop. So third grade math, 95 divided by 8, right? I put it under the little bracket here. This is, I'm old, so we do this the old school way of long division. And I come up with 11 point something, something, something. Well, I don't want to know the decimal values here. What I do want to know is what the remainder is. So in early mathematics, I remember we didn't care about the decimal points. We cared about the remainder. Well, the remainder is the modulus. So we're just looking for the remainder of a division problem here with our prime numbers, or with these numbers in our formula. So if I plug in the numbers here, 17 to the power of 8 mod 149, I get 5. All right, once I have that value, I send that over to the server. The server then stores that in memory, and it does this equation for itself. All right, so that 5 that we calculated, that is the encrypted key. It's not really the encrypted key, but it's a component that we're going to use to generate the key. Server is going to do the same exact calculation. All right, so server is going to run the G value of the public key, raises to the power of the private key, mod P, and this time we get 16. So now the server sends its key, its encrypted key, over to the client, and now we're going to do the math that makes this all work. The math that makes this work here is we take the encrypted key that each device sent, we raise it to the power of the private key, mod P, from our public key. And when we do this, on the client side, we get 129, and on the server side, we get 129. Now 129 becomes our session key on both sides. All right, so the 129 value here, this is what's used now to do our bulk encryption with AES or SSL20. All right, and notice that we've never sent the 129 across the wire. It's never been sent across the wire, and the only way to generate 129 is if the private key on the client side is 8 and the private key on the server side is 6. So unless we know the private keys of the server and the client, we're never going to be able to generate that number. Now, does that mean Diffie-Hellman isn't corruptible? No, it has to do with the way the random numbers are generated for both RSA and for Diffie-Hellman. We really don't want to be using Diffie-Hellman because of its implementation is the thing that's potentially corruptible here. It's the thing that we can attack is the implementation of these protocols. So this is Diffie-Hellman's operation. We use that to get our key, so then we can go do our symmetric key encryption using AES or SSL20. If you notice, I'm not talking about triple DES, and we'll get to that in a second. So with TLS encryption, we have TLS version 1.2 or 1.3. Let's look at the differences that we can use here for the key exchange. For 1.2, I can use RSA, Rivis Shamir Edelman. That's the public key encrypts, the private key decrypts. I can use Diffie-Hellman, and I can use elliptical curve Diffie-Hellman. Well, it's advised that we do not use RSA because the implementation has potential security flaws. It's advised that we don't use Diffie-Hellman that I just explained because of its implementation has potential security flaws, which means that we're left with elliptical curve Diffie-Hellman. So in TLS 1.2, we can negotiate this, all right? We can negotiate which key exchange we're going to use. In TLS 1.3, we don't have that option. We use elliptical curve Diffie-Hellman or we don't encrypt. So with TLS 1.3, we're using ECDHE. With 1.2, we should be using ECDHE for our key exchange. So where does that leave us here? Leaves us here talking about elliptical curve Diffie-Hellman. All right, so I have oversimplified this concept to a point of it being almost not real, But my goal here was to leave you guys with a visualization of what's happening with elliptical curve Diffie-Hellman, so that when you walk away and you're thinking about what's happening with TLS, you at least have this visualization to work off of without having to do any kind of hardcore math. So this is an elliptical curve. Elliptical curves can be represented by very specific algebraic formulas. Here we have different curve types that mathematicians have come up with and labeled. When we're using elliptical curve, the curve is going to be our public key. All right, and when we pick our public key, we draw a line through the curve, and that allows us to pick some points on the curve that give us some numerical values that we can use for our encryption. All right, so we take this curve with the line drawn through it. We're going to mathematically combine that with our private key, and that is going to result in the encrypted key. So remember from Diffie-Hellman, we ran it through the G to the power of A mod P. This is kind of the same thing here to generate that encrypted key. Then what we can do is we can take that curve with the line plus our encrypted key that we've calculated. We can send that over to the server. The server is going to repeat this process. It's going to take that curve, which is our public key, right? Combine it with its private key, come up with its own encrypted key. We're going to send that back to the client. And now we have all the components that we need in order to calculate a symmetric key. All right, so this is going to result in a symmetric key. So elliptical curve is more efficient. We can get a stronger key with less computation, and its implementation is less corruptible than with RSA or with Diffie-Hellman. So this is the key exchange that's happening. And it's a really important part of the process, but it's not the part of the process that's doing the encryption. This is just to generate the key. So we have the key exchange, then we're going to go do the data encryption with the key that we've generated. we typically have 3 options here with some supporting roles for some other hash algorithms to validate our encryption. But we can use triple DES, we can use AES, or we can use SHA-20. Now, we don't use triple DES anymore. It's not recommended. We developed AES in the early 2000s explicitly to replace triple DES. So we don't want to use triple DES anymore either, which leaves us using AES or SHA-20. If we're using TLS 1.3, we can use either AES or SHA-20 in our encryption. So now we get to another component here, and that's handshake integrity. So in order to make sure that no one has corrupted, or in order to make sure that no one has interfered with our communication, like a man in the middle, we have some handshake integrity that we're implementing here to make sure that no one's touched our stuff, right? So what we do is we take little pieces of the handshake and we run it through a hash algorithm, and we put the result of that hash inside of one of the handshake messages. And that way, both the client and the server can validate to see if somebody tampered with the handshake message by checking the hash calculation in the end. We can use SHA, SHA-256, or SHA-384 to do this. It's recommended to use 256 or 384 bit values to do our handshake integrity. All right, so that's going to validate that no one has tampered with our data as it's traversed the wire and made some modifications to it. And so far, I've only talked about the certificate being used in this process once, really, right? And that's when we talked about Diffie-Hellman using the P and G values for Diffie-Hellman. So we still have this other component here, and that's server authenticity. We're going to use that certificate to validate that the server is who it says it is, right? So the server certificate can be used for RSA encryption. That's public key encrypts, private key decrypts. We're not using that. We can have the public key, the P and G values for Diffie-Hellman, but ideally we're not using Diffie-Hellman anymore, which means that really we're using the certificate to validate that the server is who it says it is through this certificate chain and signed certificates. So there's a whole lot to learn about certificates. We spent probably 2 or 3 hours on it in Sake's class yesterday, talking specifically about certificates. I'm going to spend almost no time talking about certificates here. It's an important topic, but more than anything, I wanted this session to be about engineers being able to understand what's happening with the encryption and to be able to decrypt their traffic effectively to do some troubleshooting or just for their own curiosity. So what's next here? Let's talk about our handshakes, all right? So TLS's handshake, we're going to look at 1.2 first, and then we're going to look at what 1.3 adds to this, or what it subtracts from this and makes it more efficient. So in TLS 1.2, the client sends a hello message. That's the browser saying, hey, server, these are the protocols I support. This is what I'd like to do. If it's using elliptical curve Diffie-Hellman, it'll send the curve type and the encrypted key. It'll send that right away in the client hello message. And it allows the server to figure out what it can negotiate then with the client. So then the server sends a hello message back and it says, okay, let's use these protocols to do our encryption, right? We're going to use elliptical curve Diffie-Hellman with AES 256 encryption and SHA-384, right? So the server will send back the cipher suite that it chooses. The server is then going to send its certificate. It's going to send the server's key if it's using Diffie-Hellman. And then the server is going to say, I'm done with the hello. The client then sends back a message saying, here's my key if we're using Diffie-Hellman. It's going to send the change cipher spec, which means that everything is set now. We're ready to start encrypting. And it says the handshake is finished now. I'm ready to encrypt. And it sends our handshake integrity information in that finish message. Server does the same thing, sends the change cipher spec, the handshake finish message. And now we're ready to use our encryption protocols to actually do our bulk encryption of data. This is where our usernames and passwords get encrypted. The website data gets encrypted, credit card information, all that gets encrypted now over the public wire. So in TLS 1.3, this changes. TLS 1.3 is a much more efficient protocol. What happens with TLS 1.3 is we send the client hello message. In this client hello message, we're going to negotiate the bulk encryption and handshake integrity protocols, but we're not going to be able to negotiate the key exchange, right? The key exchange is fixed. So it's fixed to Diffie-Hellman, elliptical curve Diffie-Hellman. So when we send this client hello, right in the hello message is going to be the elliptical curve that was chosen, plus the encrypted key, as well as the other cipher suites that the client supports. So the client key is sent right away with the client hello message. So the server can use this to its advantage. When the server sends the hello message, the server sends the server key as well. It also says, let's use this cipher suite. Let's use AES 256, SHA 384 for our encryption and handshake integrity. And now after this moment, the server and the client can start to send encrypted messages, which means that when the server sends its certificate over in TLS 1.3, the certificate is actually encrypted. So if you're man in the middling and spying on this, you don't have access to the certificate anymore. It's totally encrypted, as is the rest of our handshake message, which is basically going to be this handshake finish message. The client then sends a handshake finish, and now we're ready to start our bulk encryption of data. All right, so the TLS 1.3 handshake is much, much more efficient than the TLS 1.2 handshake. Do you guys have any questions so far? You can pop those into the Q&A or into the chat if you want as we go along. I'm happy to answer any questions you guys have. Or give me thumbs up if you think this is going all right, or thumbs down if you want to know information, or whatever's needed here. So yes, Nick raised his hand. You want to, oh, there you go. Can I talk about session tickets? I can only briefly talk about session tickets in the sense that the session ticket can be used to resume a session. That's going to be a bit beyond the scope of this particular presentation. However, Peter Wu is the Wireshark expert on a lot of this. He actually writes the code for Wireshark's security, encryption, and decryption protocols. So, and he maintains all of that in there. So I would definitely ask Peter in his session. I think it's tomorrow or later this afternoon. I'm pretty sure it's tomorrow though. Dimitri is asking, how does it know to use 1.2 or 1.3? All right, so in the, we'll look at this in our, when we do the capture. In the client hello message, it will send a list of TLS protocols that it supports. So you can actually, the server will be able to determine what the client supports. The client may say, hey, I only support 1.3, and then the server will have to either talk on 1.3 or shut the session down. Or the client can say, I can talk on 1.2, 1.3, SSL version 3, or any other previous protocols, and then the server decides which one it uses. Dave is asking, how does 1.2 versus 1.3 impact TLS inspection for security devices? Right. So TLS 1.3 made it a little bit challenging for devices like a man-in-the-middle box that's explicitly used to inspect the traffic, like in a corporate firewall. And TLS 1.3 has included pieces of the 1.2 handshake in it, and it does some goofy trickery in the handshake to make it look like a TLS 1.2 message, even though it's TLS 1.3, and it leaves the function of that device unaffected. How is it possible that ECC has shorter key lengths than RSA or Diffie-Hellman and it's still secure? This is a question that is beyond my mathematical skill set. My answer to that generally is magic. And I think though, if you find Peter or Sake, they may be able to answer that. They might be able to ask that in the Discord group and get that answered. Sorry, I can't answer that. And then what else do we have? Does TLS start at 1.1 and then work its way up to 1.3? No, this goes in the beginning. When we do the decryption here in a little bit, you'll be able to see there's going to be a list that the client sends, and it's going to say, I support TLS 1.1, 1.2, 1.3, and then it's up to the server to pick the right version. And then Craig over in chat is saying if a client supports TLS 1.2 and 1.3 SSL, and server can support all of them, does the server choose the most secure? There are configuration settings on the server typically to choose the priority of which one you're going to use. Ideally, yes, it would choose 1.3 over anything less if it had that option. So, all right. Sorry, some of those questions were a bit beyond my scope, but I'm hopeful that you can find some other really awesome nerds here at SharkFest to help you answer those. So, all right, let's move on here. Oh, thank you for putting Peter Wu's session is tomorrow at what is that? 20 is 11 a.m. Pacific time tomorrow. So, all right, so let's go into Wireshark here, and take a look at some information.
I think there is another question in the Q&A.
All right, do I have to scroll down maybe? Let's see. Oh, there we go. Any tips on decrypting TLS SRTP? Yeah, let's see if this answers your question. If you can capture the session key, you can definitely do the decryption of any TLS transaction. I don't know the SRTP protocol, but if we're using TLS, and we can capture the session key, we can do any of that. There's several ways to do that. I'm going to show you how to do it using Firefox and Chrome on both Mac and Windows. There are ways that there are utilities out there that we can get that will actually grab the session keys right from your memory and store it. There's other ways to do this with the man in the middle box. A lot of it is beyond the scope of this particular presentation. But let's see if what I'm about to show you will answer your question. So, all right. So let's start with Windows. Natalia, can you see my Windows screen up now? Does it say Pluralsight? Okay. All right, so if we want to capture our session keys using Windows, what we have to do is we have to create an environment variable. So what I can do here is just search in my window here for environment variable, edit system variables. And what I do is I go to environment variables, and I need to add this variable in the user variables called SSL key log file. So let me delete this and I'll re-add it so you can see exactly how to do that. You click new, all caps, you type SSL key log file, and then we browse for the file. And I'm just putting this in my documents folder, and I called it SSL key log. I hit open and hit OK. You can call it anything you want. Does not have to be called SSL keylog.log. It can be called any question there. or any file there. Oops. The questions aren't scrolling automatically for me here, so. Okay, so this is for VoIP transactions. Okay, so yeah, unless your SIP client will dump the session keys, or you're using a man in the middle box that won't add too much latency to your calls then. Thank you, Wes. Okay, so we add this SSL keylog variable into Windows. We hit OK. And now, I'm actually going to delete that SSL keylog file. And then I'm going to open up and start up Wireshark, start a capture. I'm going to start up Chrome or Firefox. This will not work with Edge. It won't work with Edge. So I'll start up Firefox. And once I start up Firefox, we're going to see that the SSL keylog file gets generated. Just boom. Once it starts running, the SSL keylog file gets generated. Thanks, Firefox. Not right now. Let's go to https wireshark.org. And then we can close this browser. Close this one. And we can go over to Wireshark. And right now, all of our TLS conversations here are encrypted. And I can tell they're encrypted because, let's just do a TLS search here. I can tell they're encrypted because we see this information where it says application data. And if we open up the details of that, it's going to say it's HTTP over TLS, and then it gives us this encrypted application data. So in order to decrypt this, we just have to grab that session key and apply and insert it into Wireshark. So to do that, I'm going to go to I'm going to right click on anything that says TLS in here. I'm going to right click on it, go to Protocol Preferences, and open TLS Preferences. I'm going to browse for the keylog file, select it, hit open, hit OK, and now it didn't decrypt it. There we go. Actually, it did decrypt it. Here's some decrypted messages. Oh, it just took a second. So suddenly now, instead of having application data, now the encrypted application data still shows up in our detail, but then it also shows us our HTTP data. And now we can start to use that to actually see exactly what's happening here in our conversations. All right, so if I try to find my wireshark.org one here, let's do frame contains Wireshark. That'll show me here's my TLS hello. Let's do a follow TCP stream on there. Or as Jasper likes to do, conversation filter of TCP. And now we can see this conversation. It's using TLS 1.3 to do this. So let's take a look at this handshake quickly. All right, TLS 1.3, we send the client hello message, right? We have SYN, SYN-ACK, ACK, and then the client sends the hello message. So this is Firefox sending the client hello message. Let's take a look what's inside of there. So inside of the client hello, we have some general information. Then we have the cipher suites that are supported. All right. The ones that are TLS 1.3 are going to be the first ones. And there's only 3 of them here. So the first 3 here are TLS using AES 128, SHA-256, SHA-20, SHA-256, or AES 256, SHA-384. So those are our 3 options for TLS 1.3. How do I know those are the 3? Well, those 3 do not have a key exchange protocol listed, right? Because in 1.3, we already know what the key exchange protocol is. However, we can tell that this client also supports protocols besides TLS 1.3 because it has all of these options here. We can use elliptical curve Diffie-Hellman, or we even have RSA options, all right? And the reason that we have these RSA options is that we can actually configure TLS 1.2 on the server side to use RSA, and then we don't have to worry about capturing our session keys. We can go grab the private key from the server, put that into Wireshark to do our decryption. So a lot of engineers like to do testing with this, but it's not recommended that we do this with production equipment. Natalia, can you just read that question so I don't have to swipe between my OSs here?
Manfred says, you may check also the commercial solution using a tiny sensor agent, which captures the TLS session keys from clients or server's memory and transfers it.
Yes.
Also encrypted.
100%. Yes. Yes, absolutely. Yes. That's exactly the solution that you'd most likely want for that, for the voice over IP conversations. 100%. Yes. Yeah. Last year, one of the sponsors was the company that does this, and the name is escaping me right now. So if somebody can remember that name and type it into the chat, I would be grateful.
I think he wrote it down. Nubeva?
Nubeva, yes.
Okay.
That's one of them. There's another one out there too. Okay, so going on with this. So we have, no, not Profitap. That's a different one. They may be able to do that, but this one is it's a client that actually gets installed right on your device, and it goes and grabs your keys out of memory. All right, let's move on with this. So right away, we can tell, since this client is supporting all these options using where we can choose the version, where we can choose the key exchange protocol, we can tell that this is going to support more than just 1.3. So if you go down here, we can see let's see, our key share information. If we look at the key share information, here is where we're sharing our elliptical curve key plus the curve and the points on the curve. So this is our public key plus our encrypted key information that we can use to do ECDHE key exchange. And by default, our Firefox client automatically chooses to send 2 separate keys. So it gives the server an option to use either X25519 curve or SECP256R1. So the server then can pick which one it wants to use if it's going to use Diffie-Hellman or elliptical curve Diffie-Hellman. All right, so this is sent right in the hello message. So if we end up choosing TLS 1.3, the server already has the key information from the client. Supported versions. All right, there's a couple questions about this. Here is Firefox telling the server which TLS versions it supports. Now, the current version of Firefox only supports 1.2 and 1.3. However, you can go into some expert configuration spots in Firefox and actually turn on older protocols if you choose to do that. All right, but by default right now, TLS is only supporting, or sorry, Firefox is only supporting TLS 1.2 and 1.3. The rest of this although it's important, I'm going to leave that to you guys to go investigate that a little bit more. Let's go take a look at what the server said now. So the server came back and said, all right, sounds good, client. We're going to pick version 1.2, or are we? Well, version 1.2 here isn't real. All right, this isn't actually using version 1.2. How do I know this? How would you know this? Well, look at the cipher suite that was chosen here. We can tell right away from the cipher suite that was chosen that this is not TLS 1.2. And how do I know that? There is no key exchange protocol listed here, right? We're only listing our bulk encryption and handshake integrity protocols. So, so we know that TLS 1.3 is in operation. TLS 1.2 is being stated here for those man-in-the-middle boxes, for those security devices that that are decrypting and inspecting our traffic, right? So those corporate firewalls that are inspecting the traffic, looking for nefarious information and some data loss prevention. This is set to 1.2 for that exact reason. So RSA here is, so the RS for this question from this question that popped up in chat here, is there any other algorithm than RSA to authenticate the server via certificate? Are there plans to replace RSA in the future? So as far as I understand, using RSA to generate the certificates is acceptable. Using RSA to generate the certificates, validate the certificates, this is all acceptable. The challenge comes in when we're using RSA to do the actual encryption to generate our key, right? When we're using RSA to generate the key, that's where the problem comes in. I don't believe that RSA is problematic to generate the certificates, at least not entirely yet. All right, and then thank you. Manfred says TLS 1.3 cipher suites all use the same hex number string starting with 13. And you can see that right here, 1301. All right, thank you. All right, and moving on here. So we can see then that the server is sending its key share information back to the client. All right, so the server is saying, okay, great, we're going to use X25519. Here's my key information. Right, and now after this, everything is going to be encrypted after this. Now, it's not going to look like it's encrypted here because I've already put in the session key, but everything in our handshake after this is going to be encrypted, including our certificate, right? So here the server is now sending the certificate information to the client and saying, yep, we're all done now. Then the client comes back and says, we're all done. And now everything after this is encrypted. All right, so here we can see HTTP kicking in and transferring our website. We can see all of the HTTP information, TCP information. None of this is encrypted now because we put in that session key. All right, let's go take a look at how to do this in Mac. And then we will we'll look at how to do this on the Mac. We'll look at a TLS 1.2 handshake and see how it's a little bit different. And then I'll answer some questions and we can start to wrap up the presentation. So here I am back on my Mac. Now, in order to get the session keys on a Mac, we have to launch Firefox from a command line. So we're going to use the command here. We type in export SSL key log file equal to, and then we give it a location. So I'm going to do this the easy way here. And just drag this right over here. There we go. Next, I want to start Firefox. Open -A, and then I go over here and find Firefox and hit enter. That should launch Firefox for us. Let me start up Wireshark. Start a capture. Thank you, Stefan. Oh, I forgot the same thing here. Can you see, you guys can see my face, I'm guessing? Yeah. I forgot to put this on. Oh, and you can't even see it with my virtual background. Look at that. Rawr. Oh, it's just too hot to have that on right now, so. All right. Let's start up a capture. Oh, I did start a capture. Oh, and that was the wrong interface that I started on. All right. I think this is it here. I have to find my interface. Just a moment.
There are 2 new questions. Dave asks if it doesn't work with Chrome on Mac, or is it only Firefox? Yeah, it's the same question.
It'll work with Chrome on Mac. Yeah, Firefox and Chrome both work. I don't think Safari works, but I have not tried it. We can test that here in just a minute. So USB. There it is. All right. So let's go to https wireshark.org. There we go. Let's close this. Stop our capture, which is a disaster because of the Zoom, all the Zoom messages. Let's go find it. Wireshark, or frame contains Wireshark. There we go. Conversation filter, TCP. All right, so let's take a look at this. So is this session encrypted? It appears so, right? Because we're not seeing any HTTP data. We can look on our sidebar here and see that it's all purple. And there's no green in there. If there's some green in there, that would mean that it would be decrypted. Marcus is asking if it would work with Firefox or Chrome on Linux, and the answer is yes. This should work the same exact way on Linux. All right. So let's decrypt this traffic. Let's go put our session key in here. Remember, we click anywhere on transport layer security. Open our preferences. Let's go grab our session key from my documents folder. Hit open. It'll take a second to process that. And there we go. Session is decrypted. All right, let's take a look at our TLS 1.2. Oh, this is TLS 1.3 again, because I captured the same website, of course. But we can go grab a 1.2 as well. So this is how we get our session keys in on a Mac or on Linux. Let's test this with Safari quick to see if it works. I'm going to go delete my session key. I'm going to delete that file.
Somebody is asking, sorry, Ross.
Oh, no, you're good.
Somebody's asking if it maybe work also with the new Windows Edge, which is now running Chromium in the background.
Yes, we just did this test yesterday in Sake's class, and the answer was a definite no. It does not work. It doesn't. When I delete the SSL keylog file like this, and I opened up Edge, it did not populate the keylog file. Let's see if it works with Safari here. I don't think this is going to work. Oh, where'd it go? No, so Safari, well, let's go to a website. No, so Safari is not generating this either. And it does not work in Edge either. In fact, I can show you. It's easy enough to just show you guys that it doesn't work. And there may be another way to get that file, but I don't know how it is using Edge. So there we go. I deleted that file. If I open up Microsoft Edge, it should have already populated that keylog file by this point. So yeah, it doesn't populate the file. If I launch Firefox or Chrome, it instantaneously populates it. Right there it is already. So it doesn't work on Edge, doesn't work on Safari. You'd have to use a different solution to get there. All right, let's take a look at a 1.2 conversation, and then I'll see if there's any other questions remaining, and we can start wrapping this up. So in that link I sent you, or the link in my OneNote, there's all kinds of examples here of different encryption protocols. Let's do one with Diffie-Hellman ephemeral. Let's make sure I have that keylog file. Now we'll have to do this one. So this is a capture I did from pluralsight.com. It's using TLS 1.2. If we take a look at that client hello message, take a look at the client hello message, we're going to see that, let's look at our supported protocols here. Well, we'll just start off with, did I select the client? Okay, there's the client hello. Cipher suites, here we go. This is what I was looking for. It's right in front of my nose. So our cipher suites this time, are we going to be using, do we have an option to use 1.3 in this case? You can, Jorg is saying maybe an only slightly outdated link on how to capture the Wireshark. Okay, so maybe that'll go through, oh, okay, I see. There's a question above that. My bad. What was the command string you used to put into the terminal? It was export SSL keylog file. Let's just type that in here. There we go. Okay. Let's make this bigger again. Okay. So here, do we even have an option here of using TLS 1.3? And the answer is likely no. How do we know this? Well, one, the hex values for our protocols, just as like somebody pointed out earlier, none of these have a 1.3 in front of them. And two, if we just look at the name of it, none of them have, or all of them have a key exchange protocol listed here. So we're only going to have an option to use at least TLS 1.2, likely not TLS 1.3. Looks like I have some questions coming in. I'll get to those in just a second here. Supported groups. Here's for our elliptical curve supported groups. So here with TLS 1.2, we don't need to ask the server which version we're going to use. It's going to use whatever it can use, right? Server comes back with its hello message. This time the server hello says, okay, we're going to use TLS 1.2. We're going to use elliptical curve, Diffie-Hellman ephemeral with AES 128 and SHA 256 here. Right, so we're going to be using the elliptical curve. It gives us the point format that we're going to use here as well. The server then sends its certificate, the key exchange information. The client then sends its certificate, key exchange information, and says, okay, I'm all done. The server says, okay, I'm all done. And then we have our application data, which is our encrypted data. Safari and iOS does not have this feature natively, no. What are you going to use to grab the session token? I don't understand the question. So session keys, you don't have to provide the private key to decrypt. No, it's literally the key that's being used to decrypt it. Right? The only time we're going to use that private key is with RSA encryption. So this is Jeff's question. So session keys, you don't have to provide the private key. No, you do not. That is just for RSA encryption using Wireshark. Is it just Wireshark? I don't know. Roger, if you can be more clear on your question, I'll see if I can answer it. I guess Rick is asking, I guess a firewall that does not deep packet inspection by doing this man in the middle is pretty much not doable since the cert is now presented after the encryption started. No, because that device is the man in the middle. It's terminating those firewall devices terminate the SSL connection, right? So instead of having client, my client here, my desktop that I'm using to do the captures, instead of that having a full connection all the way to wireshark.org and back again, that's not actually happening. The client is negotiating its SSL session between the client and the man in the middle box, the firewall box, and then the firewall box is doing another session between the firewall box and wireshark.org. So in the middle there, it's actually unencrypted at that point in time. So we get the session keys because the box in the middle has the session keys. It's generating them for both the client side and the server side communication. All right. Hopefully that makes sense, Rick. Can you confirm that TLS 1.3 has to be in an extension supported version? Otherwise, it's not available during the handshake. I believe it has to be in that it's extension or it will not be supported because, you know, that the client hello, if we just compare the client hellos here, this client hello is missing information that's required to do elliptical curve Diffie-Hellman. And hopefully I don't put my foot in my mouth here, but there is no key exchange sent here. There's no elliptical curve key exchange sent in this hello message when it's only using 1.2. So it has to, that extension does have to be there in order to get this to work correctly. You mentioned that with TLS 1.2, you could get the key from the server. Where do you get that? With TLS 1.2, you can get the key from the server if you are using RSA to do your key exchange. Only if you're using RSA to do your key exchange, which we don't advise doing in a non-prod environment. Is there any similar technique to decrypt SSH sessions and look into the date transmitted in the SSH tunnel? I do not know. I personally don't know how to do that. Some interesting information on iOS for decrypting using TLS session keys. All right, great. Thank you for posting that. All right, and Gabriel saying, I tested after Sake's class yesterday and it works in the new Edge. I assume whoever tested it was using an older version. I just did it with version 86 and the session keys are logged. Okay, excellent. Maybe I do have an older version of Chrome or of Edge. Let's take a look. I've literally never used this program. Not ever once. Is there an about here? Go away. Like I don't know what's happening. Yeah, no, just stop. All right. Yeah, I don't know. I don't know where the about is. Yeah, it's fine. Okay, it's definitely an old Edge. All right, so everybody is confirming that it does work with the new Edge. I just didn't have mine updated, so thank you for that. Is there a site to walk you through the Windows SSL keylog setup? This session is being recorded. It will be available on YouTube. I go through the same process in last year's session 2 for SharkFest 19 in the US. So you can go back and watch that as well. Ross, I think you're using the old Edge. Yeah, I agree. I agree, Manfred. I'm very likely using the old version of Edge on there. Settings help. Thank you. Got it. Thank you. Clippy, new Clippy. Did I type that wrong? Well, it did a Bing search for me, which is exactly what I wanted. All right. Well, thank you guys for the help on that. It's probably for the newer version of Edge. You're right on. Thanks for the help on that. You guys, if we were doing this in person, we could all go have a beer after this and you could razz me on my inability to use that browser. So. All right, do we have any other questions that I can answer? I really hope you guys found this useful. I realize that this didn't go into, this wasn't a deep dive, wasn't intended to be a deep dive. This was supposed to be an opportunity for everybody to get a visual idea of what's happening with TLS so that you can use this information to actually do your work better and have a better understanding and not have to go online and listen to somebody tell you that in TLS, the public key encrypts the data and the private key decrypts it, because that doesn't help you at all. So, all right, we have 5 minutes left here. So if there's no other questions, if there's a last minute question you have, fire away. I really hope you enjoyed it. Here, let me put the feedback thing up here so you can leave me some messages and tell me how great or how awful I did. So you can scan that on your phone. I would wear the shark hat for the entire presentation, everybody, but man, this thing is hot. It's so hot, and it's about like, it's like 75 or 80 degrees and super humid here right now. So I'll leave you with da 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 da. All right, good luck, everybody. I know you're all around the world. I know this was some of you had to wake up super early or stay up super late for this. I'm so grateful for everybody attending. Yes, Dent, that information was right at the beginning of the chat. Right in the beginning of the chat, there was the link to my OneNote. Let's see if I can put it in here again quickly before the session ends. I'm glad you all enjoyed it. Thanks, everybody.